We've been using data visualization to see how we can visualize the relationship between two variables. We are now going to use data visualization to visualize one variable. And you might think, what's the point? There's nothing to compare against. But by visualizing a variable's shape and spread, we can really get a sense of what that variable is doing and the story behind that variable. We're going to look at two plot types in particular, a histogram and a box plot. And both of these visualize shape and spread of data. How would we construct a histogram of this set of data here? So we have a load of numbers and we want to be able to see what is the shape and spread of this data. So we've got some measures of spread we could use, but we want to visualize that now instead. So for a histogram, what we're going to do is we're going to look at the range of our data and split it up into equally sized bins. So our data here is roughly between 0 and 60, so we're going to split it up into bins of 10, so 0 to 10, 10 to 20, 20 to 30 and so on. And then we are going to keep a tally of how many observations in our data set belong to each of these bins. For example, 17 here belongs to the bin 10 to 20. And now we've got that tally, we can see immediately this tally table has visualized our data for us. We can see immediately we have a lot of data points around the sort of 10 to 30 area. We have a little bit of data points before that, and we don't have many data points above that. And the further away we go from that initial cluster, the less data points we are getting. And that does a really good job of visualizing our data. And that's essentially what a histogram does. So now we can convert this to a histogram by drawing this on a axis like we've been doing before. So this would be the histogram of that data set, and you can see the shape of this histogram looks exactly like the tally table we just had. So we have an x-axis, and the x-axis represents the values of our data set, and the y-axis represents how many things are in each bin, the tally, the frequency. And then we've drawn what looks like a bar chart, but it isn't a bar chart. So we've drawn what looks like a bar chart saying how many values were in each bin. And by doing so, we get this idea of shape. The taller bars show there's a lot of data in that range, and the shorter bars show there's not much data in that range. There are some main differences between a bar chart and a histogram though. First, conceptually. Remember, a bar chart was plotting two variables against each other, nominal ordinal data against a number which was ratio data. Whereas now what we are doing, we are only visualizing one variable and its relationship to itself, its shape and spread, the distribution of that data. Aesthetically though, histograms do look different from bar charts. So some of the things I want to point out here, in bar charts, the bars had gaps between them, and that was to emphasize that you were dealing with nominal or ordinal data, and the nominal and ordinal values don't sort of run into each other. Here, our bars represent bins, and the bins do run into each other. The end of one bin is the start of another bin, so they do sort of run into each other, so there are no gaps between our bars here. The second thing I'd like to draw your attention to is the x-axis. Notice the x-axis, the numbers along the x-axis, is values of our variable. It's not every value, just like any other chart. We do not label every bar with what bin they represent. We haven't labelled the first bar there 0 to 10. We haven't labelled the second bar there 10 to 20 and so on. We haven't even just labelled the endpoints 0, 10, 20, 30. We could have done that and that would have been completely valid. But what I've done here is I've just chosen some equally spaced numbers to represent roughly where things are. What you cannot do is label each bar 0 to 10, 10 to 20, 20 to 30 and so on. Do not do that. That is not a histogram. The y-axis is the frequency, how many things appear in each of these bins. Now the sizes of bins in relation to each other is what's important here. We can see there's lots of data around the 20 to 30 and there's not much data at all around the 50 to 60. It doesn't particularly matter what the exact count is, because your count is going to depend on the bin sizes. The larger your bins, the more stuff's going to go in the bin. The smaller the bins, the less stuff's going to go in the bin. And some people even normalize it so that when you add up the size of all those bins, it adds to 1 or 100% or something like that. So the actual values on the y-axis doesn't matter. We could have left that blank and that would have been a completely fine histogram, and you will see that elsewhere. But I recommend for you, keep the count there. It makes it much clearer so we can understand this data analysis a bit more. Histograms show spread and shape. So the spread here, we can immediately see how spread out our data is. We can see a minimum value, we can see a maximum value, we can see where roughly most of the values are and so on. It also gives us a measure of shape. So let's have a look at how we would interpret the shape of a histogram. One of the first things we can do is interpret the skewness of a histogram. So I've used the word skewness before in videos, but formally, what is skewness? It's how wonky the dataset is. So a really wonky dataset to one side would have a positive skew. A really symmetrical dataset wouldn't have any skew. And a really wonky dataset to the other side would have a negative skew. That's not very precise. So how can I be a bit more precise? Well, when things have no skew at all, the mean and the median are equal to each other, or as close to equal as they can be. When things are symmetric, the value with the minimum distance to every other point is going to be in the middle, and the median is in the middle. So when there's no skew, when things are symmetric, the mean and the median are roughly equal to each other. When you have positive skew, you have a lot of big numbers which drag the mean away from the median. So the mean is going to be bigger than the median when you have positive skew. And then the opposite, when you have negative skew, you have these small numbers which are going to drag the mean away from the middle. So the median is going to be bigger than the mean in this case. We can actually come up with a number to represent that, and there's lots of different ways of doing that. The one I'm going to show you is called Pearson's second skewness coefficient. We say that skewness is going to be equal to 3 lots of the mean minus the median divided by the standard deviation. And why do we do that? Well, if you think about mean minus median, when we've got positive skew and the mean is bigger than the median, then mean minus median is going to be positive. And when we have negative skew, when the mean is smaller than the median, then mean minus median is going to be negative. So already this formula gives us the sign, gives us whether it's positive or negative skew. The size of the skew, so how skewed it is it very wonky or slightly wonky? That comes from the size of this number. But in order to do that, we need to normalize by how spread out the data is. So we divide by the standard deviation. And then to make some maths work in the background, which I'm not going to explain, we also need to multiply it all by 3. So 3 lots of the mean minus the median, all divided by the standard deviation, is going to give you a number which represents skewness. If it's big and negative, you have a large negative skew. If it's moderate and negative, you have a moderate negative skew. If it's 0, you have no skew. And if it's large and positive, you have a large positive skew. So it's really interpretable. Another measure of shape we can talk about is kurtosis. And kurtosis is roughly how pointy is our data set. So you can see here I've given some examples of low kurtosis, that's a very flat data set. Moderate kurtosis is a very standard sort of bell curve data set. And high kurtosis is very pointy. A bit more formally, kurtosis is looking at the tails, the very end points of the data set. In low kurtosis, there's lots of values in the end points. In high kurtosis, there's not much values in the endpoints. Again, we can assign a number to kurtosis, and the maths to work this out is a little bit more involved, so I'm not going to show that to you here. But if you do see a number attached to kurtosis, that's always going to be a positive number. And in general, we always compare to that standard bell curve, the normal distribution, because that has a kurtosis of 3. So if you've got a number that's smaller than 3, you're going to be flatter than the normal curve. And if you've got a number that's higher than 3, you're going to be more pointy than the normal curve. Another really useful plot for being able to visualize spread and shape is called a box and whisker plot, or more informally, a box plot. And a box plot looks like this thing here. So you have an axis, and that axis represents the values of your dataset. And you have this boxy shape thing which looks a bit like a syringe. And we can read this, and what this is a visual representation of some summary statistics. The very end points are the minimum and maximum values of your dataset. So here the minimum is about 1.5 and the maximum is about 12. The other 3 vertical lines represent the first quartile, the median or the second quartile, and then the third quartile. So we can immediately see where does 0% of the data, 25% of the data, 50% of the data, 75% of the data, and 100% of the data all lie below. These are useful for seeing spread and shape. A big spread would mean there's a wide box plot, and a small spread would mean a bunched up narrow box plot. And it's useful for showing shape as well. So for example here, below the median we have quite a narrow range of data, and above the median we have a large range of data. So that shows that this is skewed. We have a smaller range in the lower 50% and a larger range in the bigger 50%. So we have this long tail. And again, we can show kurtosis by comparing the size of the whiskers, which is where the minimum and maximum is, to the interquartile range, that box. Box plots are also very customizable. You can keep adding more and more information. So I don't recommend you do this, but there's a few things you might see when you read data analyses. You might see extra things on a box plot, and it's useful to know about them. So the first thing to know is that the ends of the whiskers, the minimum and maximum, don't always represent the minimum and maximum, unfortunately. Sometimes they represent the minimum and maximum once we've got rid of outliers. And then the outliers, the very, very small points and the very, very big points, they'll be represented by dots or circles or stars along the same sort of height as the box plot, but where they represent the actual values on the x-axis. Another optional extra which you see, and this is something I do a lot because I find it really useful, is we can add the mean to this. In order to add the mean to this, we would add, so the mean would usually be somewhere in the box, so say about here. The mean we could denote by right in the middle of the box, along the x-axis where it's meant to denote, we could put a star or a circle there. And the other thing I've seen people do is use the height or the width of the box, the height, to denote how many data points you have. So you might have some data sets with not many data points and you'll have a very narrow box, or you might have some data points with lots of data sets and you'll have a large box. Whenever you do add these sort of optional extras in, you must be really explicit in your write-up that you've done that, because it's not obvious and it's not a standard thing to add to this. Box and whisker plots can be more useful than histograms because on the same set of axes we can compare different distributions. So for example here I have used the y-axis, which remember wasn't really used in the box plot. So now I have used the y-axis to represent some nominal data. And here I've got professions from the wizarding world, and I've used the x-axis to denote their salaries. And these box plots are the distribution of salaries of the ministry workers, gamekeepers, professors, and auras in the wizarding world. This is super useful because now we can visually see, without having to inspect summary statistics and without having to inspect the data itself, we can visually see where do these cross over, which ones have the highest median, by how much, how does the median compare to someone's maximum, and so on. We can see here that the median salary of a ministry worker is larger than the maximum salary of a gamekeeper. So we can say that 50% of ministry workers earn more than the highest paid gamekeeper. And this is the kind of stuff which would be a lot more difficult to say and analyse if we were looking at a lot of summary statistics, whereas this is immediately in front of us with a lot of box plots.